Okay, so today I would like to tell you about how chiral anomalies work in kinetic theory and in hydrodynamics. So last time we have gone through some background materials on how one can get from kinetic theory which view particle as some point-like object that move in straight line and sometimes collide with each other. How one can get from there to the theory of hydrodynamics. So just to emphasize a point that may have not been emphasized sufficiently last time, the kinetic theory works when we take average over time scale that is large compared to the interaction time. So we view interaction as some instant things that happen in an instant and describe it through some probability transition amplitude, the collision term. Hydrodynamics, on the other hand, works in a much more restricted time scale. The time scale has to be large compared to the mean free time. So we have to wait for several collisions. So here we just need to have a time that is large compared to the time when the particle collide with the other and change its direction of motion. Here we are looking at time scale that is large compared to the time that each particle suffer one collision. So hydrodynamics is a theory that works in a longer, in the longest time scale and length scale in the problem. So now,
sorry, can I just ask a very quick question about these timescales?
Yeah, sure.
Is there an implicit assumption in the validity of hydrodynamics that the mean free time has to be much larger than the interaction time? For instance, if somehow I have like some very dense, strongly interacting system where the opposite is true, can there still be a regime where hydro is valid? Or
hydro is valid there is always a regime where hydrodynamics is valid.
I see.
Take the longest microscopic time scale that would govern the process of local equilibration. Then hydrodynamics would work. Kinetic theory, on the other hand, requires certain separation, hierarchy of scales between the interactions, times, and the mean free path. So there could be a system where there is no kinetic description, but the hydrodynamic description would still be valid.
I see.
Yeah, with some kinetic coefficient that cannot be computed, but can only be measured.
Great, that makes sense. Thank you.
Yeah. Yeah. So today we are going to describe some new type of systems that has come to the attention of physicists recently, where the issues of chiral anomaly becomes important, and we are going to describe what is this chiral anomalies. Let me see. Someone having can anybody mute them? Okay.
Oh, I'm sorry.
Okay, so the system which we will be thinking about is systems called Weyl semi-metal. It's one possible system where the issues of chiral anomaly may arise. So in electronic systems, usually we do not have to use hydrodynamics in the in the sense that we are used to the term. In the system of electrons, if we have impurities, then momentum would not be conserved. But if there is a very little impurities, then we have conservation laws, conservation of energy, conservation of momentum. And people have been making solid state materials like graphene clean enough so that hydrodynamics can be applied. So the wide semi-metal is one of these new type of materials in which as we will see, there are qualitatively new features that can be seen in the hydrodynamic theory. So before talking about wide semi-metals, which is material that exists in 3 dimensions, let us talk about simplest example of anomalies that happen in one-dimensional system. So in the one dimension, let's consider the theory of fermions. So this could be electrons moving in one dimension. And let us imagine that this fermion has some dispersion relation. So for simplicity, we can think about dispersion relation like epsilon of p equal p squared over 2m. But it doesn't have to be just that. And imagine that we put a chemical potential in the system. So here it will be p, here would be epsilon. We put a chemical potential mu here. And at 0 temperature, we can think about all these energy levels to be filled with occupation number equal to 1. And these are empty. And for simplicity, I also neglect the spin of the electron. Now at low energy, the low energy degrees of freedoms in these theories are the electrons near the momentum where the energy is mu, which is called the Fermi momentum, Pf and minus Pf. Near Pf, P near plus minus Pf. So there are 2 types of low energy quasi-particles. The one, there is a left moving quasi-particle with P close to P minus Pf, and the right moving P of order Pf. Left and right refer to the direction of its velocities. Velocity is the epsilon P over dP, the group velocity of a particles, and it's positive for right moving and negative for left moving particles. Okay, so let's imagine that let's imagine the following situation. It will be also useful in the 3-dimensional case. Imagine that the interactions between the electrons goes through processes, which in Feynman diagram looks like something like this, some scattering process, where the exchange momentum Q is very small, is smaller, much smaller than Pf. Let's imagine that we engineer such an interaction. then the left-handed particle cannot become the right-handed and vice versa. Then the number of left and right-handed particles are conserved separately. Right? Because in each of these collisions, the particle momentum can change only by a very small amount, much smaller than the Fermi momentum. So here is our picture from the previous slide. PF here, all the particles here are filled. These are empty. So in a scattering process, one of these particles can jump into a state through an interaction that has a momentum that is close to it. But as we will see, as we see in this picture, this particle would still be located in the momentum region near PF. Another particle that is left moving would jump around this region, right? So in a scattering process, particles can only move in momentum space around the point PF or minus PF. It would not be able to jump from here to here. That process required a large exchange of momentum. And so the system then at low energy has two conserved charges, conserved numbers. It's number of left-handed particles and the number of right-handed particles. They are conserved separately. Now let's imagine that we turn on an electric field. An electric field, so in here we are in one dimension, so the electric field would point in the, say, in the x direction. Our system is aligned along the x direction. Now, if you look at this picture, each particle would satisfy certain equation of motion, which in an electric field, one of these equation of motion for a particle will be its momentum dot is equal to the electric field. So E dot E times E, but I set E to equal to 1. So if I have an electric field acting on acting over a time scale of delta t, then during that time of delta t, a particle would have its momentum changed by E times delta t. So these particles that are right moving, they have momentum shifted by an amount equal delta p equal E delta t. So that means these particles will move up to a new position in momentum space. And this particle will move in here. So we have a motion of particle in momentum space to the right. E is larger than 0. That means the number of right-handed particles. So for the right-handed particle, basically the chemical potential will move up, or the Fermi momentum is moved to that direction. So recall that the number of particles, or the density, the number of particles in one dimension looks like V. It's length divided by 2 pi integral over dp, right? That's the phase space. Now, the upper limit is PF, right? And so the number of particles, so if we count the number of left-handed particle, or right-handed particle, we would take integral from 0 to PF. That gives us L divided by 2P times PF. It's number of right-handed particles. But PF during time delta T, PF goes to PF plus E delta T. And so the number of right-handed particles move to that number plus L divided by 2 pi E delta T. And so we can write an equation that looks like the total change in the number of right-handed particles is equal to the volume times E divided by 2 pi. That is the rate of change of the number of right-handed particles. The left-handed particles, the situation is reversed. Particles move to larger value of P. That means they move down in energy, leading to a PF that moves to the right. That is becoming less negative. And doing this calculation, you find that the number of left-handed particles changes, but by an opposite amount. And so here we see these two conserved charges in a situation without an electric field. In an electric field, if the electric field is now not zero, only the total charge is conserved. But the difference between the charges is not conserved. And the amount of the rate of non-conservation of that, it's called that the axial charge. We will use this terminology. The rate of conservation of the axial charge is not arbitrary. It's completely controlled by the electric field that we turn on. So this is an example of what in quantum field theory is called anomalies or quantum anomalies. Quantum anomalies, roughly speaking, is what happens when the theory has some symmetry or conserved charges, but these conserved charges is no longer conserved in external field. Now, this is the simplest one-dimensional version of anomalies. I want to describe to you now a more interesting, non-trivial example of anomalies occurring in 3 spatial dimensions. So let us imagine, and that is what actually happens in some materials, that we have electrons or some fermions, low energy, some fermionic degrees of freedom, whose energy as a function of momentum has the so-called Dirac nodes. You can think about that as some point in momentum space. So here I'm drawing. You have to imagine that as a 3-dimensional picture. Energy as a function of P And the Dirac node can be imagined as the statement that near some point P equal to P0, the Hamiltonian, effective Hamiltonian for our system looks like a Dirac Hamiltonian, which is sigma dot P minus P naught. So it's a 2x2 matrix. In the language of solid state physics, that means we have two different bands that crosses at one point. So this two bands correspond to the two two vector in the Hilbert space in which this H act that crosses each other at P equal P0. And let me renormalize this P naught to 0. So just shift the origin of P space to P0 to make formula simpler. So here there is one velocity that I have to write Pf to make the Hamiltonian having the dimension of energy. So this Hamiltonian is very easy to diagonalize, right? So we have H equal to Vf times sigma dot P, and let me write it down. Sigma are the Pauli matrices. So here I have Pz, Px plus Ipy, Px minus pi Py, Pz. This is this matrix has two eigenvalues.
Sorry.
Yeah.
Do you miss a minus in front of the second PV?
Minus, yeah. Thank you. So this Hamiltonian has two eigenvalues. One is epsilon P equal plus Vf times absolute value of P, and the other is epsilon P equal minus Vf, absolute value of P, and that is this band that I'm drawing here. These are the negative energy state, and these are positive energy. So here, energy, when I wrote this Hamiltonian, I count this point as having zero energy.
Sorry, this is probably a very naive question, but how is the fact that the Dirac Hamiltonian is a 2x2 matrix consistent with the fact that there are no 2D representations of the Clifford algebra in 3+1 dimensions?
So so you can have in 3-dimension you can have matrices gamma, right? So you want to have gamma whose anti-commutator is equal. So this is what you want, right? Or minus G mu nu. So you can have that if you break parity. So you have say gamma 0 equal like sigma 3, yeah. Gamma 1, gamma 2 is like sigma 1, sigma 2. So that would you choose one chirality. So here actually what is just one choice of chirality.
Right.
So we mentioned that at the end that this units an even number of these Dirac nodes.
Right.
But let's just look at the in a real material. So running ahead in the real material, we always have at least another Dirac node. But let's concentrate our attention, like in the one-dimensional case, in the degrees of freedom near one of these nodes. So they would have positive or negative energy, and let me imagine that for the sake of simplicity, let's imagine that I have some kind of some chemical potential mu here that is positive, right? And imagine that my quasi-particles are all near the Fermi level. So here would be my quasi-particle would have energy around chemical potential mu plus minus something that is smaller than mu. And then let's assume all quasi-particle have positive energy. That means that all these negative energy states are completely filled and becomes inert from the point of view of our discussion. Maybe even some of these positive energy states are also completely filled, and we don't have to think about them. The low energy physics is dominated by some band of energy near chemical potential. Typically in a system at finite temperature, the width of this band is given by the temperature. Okay, so here basically we are saying that the temperature, we assume a simple simplified regime. T is much less than mu. So these would be quasi-particles, right? And they are characterized by a relativistic equation of dispersion relations. They move like relativistic particles with velocity vf instead of velocity of light. And so we can ask the question how one can write down the how one can write down the kinetic equations for these quasi-particles. And can we write down also hydrodynamics theory of this of a gas, these quasi-particles. Now that there is some modification to the equation of motion of this quasi-particle that would appear already, we can already see its appearance in the kinetic theory, in the kinetic description. So to see that, we let us recall one issue in one theme in quantum mechanics called the Berry phase. So the Berry phase can be illustrated in the problem of the motion of a particle in a magnetic field. Classic problems where the Berry phase can be seen already in the classical action of a particle in a magnetic field. So the classical action of a particle in magnetic field looks like this. So I have mx dot square over 2. X is the coordinates of the particle plus a at x times x dot so this is the Lagrangian or action principle from which one can derive the equation of motion of a particle in a magnetic field with the Lorentz force, etc. But if I look at this second term, right, it's integral of a times x dot, that can be rewritten as integral over the trajectory of the particle times, say, ai x. Let me write this way. term is equal to the integral along the trajectory of the particle dxi. So we think about x dot dt as dx dot with times ai x. So that corresponds to, in quantum mechanics, if we think about the action as a phase that would have to assign to a trajectory of a particle. Each trajectory would be assigned phase e to the is. The interaction of the particle with the magnetic field means that a trajectory, any trajectory would have an additional phase. And that additional phase is so exponent of I integral of dx iai. So that explains many things that happen when a particle moves in a magnetic field. This phase, when this phase shifts the classical trajectory, which is the stationary phase solution, to a new trajectory where the equation of motion now contains a Lorentz force. So a Lorentz force, in some sense, can be interpreted as the effect of the Berry phase due to the gauge field A on the classical action. And also this additional phase would give rise to things like the Aronoff-Bohm effect. So the thing that I want to tell you now here is that for a Dirac particle, there is an additional Berry phase, not associated with the magnetic field, but it can be thought of as a magnetic field in momentum space. And it leads to modified classical equation of motion. So let's see how does this Berry phase arises. So you remember when we derive the how do we derive the Feynman path integral? Derive Feynman path integral. We imagine that we follow. We take a sum of take an evolution of a particle from some point xi to some point xf, right? And then we sum over all possible intermediate state. So in each of these, we also break time into small pieces, and we basically evaluate the evolution operator that take us from some point x to another point like x plus dx. And that is what gives us the exponent of the action that take a particle from point x to point x plus delta x. It's possible to reformulate Feynman path integral so that it acts on in phase space. So here the action would be integral over dt of the Lagrangian, but the Lagrangian now have px dot minus the Hamiltonian, which is something like p squared over 2m plus some potential energy that I'm not going to write down here, but the terms a dot x can still be written down here. So then this corresponds to taking a particle, when we're doing the path integral, taking particle along, basically forming a coherent state with some value x and p, and then drag it along in momentum space. Now, if we do that in the case of Dirac particle, we will find the following things. If we take a particle with momentum p, right, and then try to move it to a place with new momentum, like p plus delta p, and here we have some evolution operator, then we have an additional phase on top of the usual terms that associated with the Hamiltonian. The additional phase here is basically the overlap between the state with momentum p plus delta p and state momentum p. And that overlap is an additional Berry phase. But now it's due to the fact that the particle move in momentum space. So let's just calculate this Berry phase. So since our energy, so the particle has positive energy, and so we have to find the eigenvalues of the following problem. Vf times, say, pz, like px plus ipy, px minus ipy, p minus z, times the eigenvector of the Hamiltonian, and let me call that u, say it's u1, u2, equal to Bf, absolute value of p, times u1, u2. If I go to spherical coordinates, for p, that is pz equal p cosine theta, px equal p cosine theta cosine phi, etc. For py, you find that is u1, u2, up to a phase looks like cosine theta over 2 sine of theta over 2 e to I phi. Basically, it's the same problem for spin 1/2 particle. The problem of diagonalizing a Hamiltonian of spin 1/2 particle in a magnetic field, except here that spin is not the real spin. It's some pseudo spin due to the fact that we have two different bands. So the Hamiltonian of a particle is a 2x2 matrix. So now we can compute the Berry phase. For that, we need to take the eigenvalue of momentum P plus delta P and multiply, take a scalar product with the same with momentum P. So here we have like cosine theta prime. So P, let me call that P in spherical coordinates. Assume it have angle theta and phi. This one has angle theta prime phi prime. Of course, cosine phi prime. Cosine theta prime e2 minus phi prime times cosine phi e2 plus phi. With theta prime equal theta plus delta theta, phi prime equal phi plus delta phi. Sine, I think this is sine. When you do this calculation, you will see that the term that's non-zero that appear here is equal to, it can be written as exponent of, can be written as 1 plus I times minus I times sine, I'm sorry, this has to be over 2, over 2, over 2, over 2, sine square theta over 2 times delta phi. So I write it as an exponent. So let me draw for you the illustration. So here we have, I draw a circle. Each of the eigenstate of the Hamiltonian with momentum P correspond to a unit vector. So I take this and then move it to another point at P plus delta P. And what we have computed is that there is a Berry phase. The Berry phase is equal to the area. Turn out that it's equal to the area of a slice of a sphere. That we form by drawing two large circles from the North Pole and then compute the area of the, like this spherical triangle that obtained this way. Up to a factor of 2. So this is the half of the area of that region. Any question so far? This is just a Berry phase. It's exactly the same Berry phase one would obtain for spin 1/2 particles when we change the direction of a magnetic field.
I had a question on the way the action was rewritten, maybe 1 or 2 whiteboards ago.
Mm-hmm.
And I guess on this one, yeah. So when it's formulated in terms of kind of mixing position and momentum, like what's the variational principle that gives you the equation of motion in this case? Like even classically, yeah.
Yeah, I think if you differentiate S with respect to P, you get an equation like X dot equal P square over M. All right. So that's one of the equation of motion. I'm sorry, P over M. X equal P over M. Now you can imagine that you integrate over P. That means solve the equation of motion over P and then put the solution here, P equal mx dot, and you get back. So you get back the usual x dot equal, so mx dot square over 2 plus a x dot. And I get back the normal action. And so this action is just equivalent to the previous one, up to a substitution of the equation of motion. So this the second equation would be delta s equal delta x equal to 0. Yeah.
I see. Okay, thanks.
Yeah, yeah. So in the Dirac case, the thing that makes it convenient to use this mixed representation is that then now we know how to incorporate the we can incorporate the Berry phase due to the motion of the particle in momentum space. So in this case, the Berry phase can be thought of, can be interpreted as an additional term in the action, besides all the term that we have before. There is another term that I can write as the I can write like dpi times some mu a ai as a function of p, similar to the integral dx I ai of x. Here I have some calligraphic a that characterizes this Berry phase in momentum space. So let me put here actually sign minus to make the future equations more symmetric. So here this a, you can read out this a here, in the polar coordinates, the a phi will be equal to sine square theta over 2. So it's like a particle that moves in a magnetic field that there are two magnetic fields. There's one acting in coordinate space and the other acts in momentum space, as if. So to compute the magnetic field, let me call that some F, calligraphic F, maybe, is curl of A. But this curl is the curl in momentum space. So here you can compute, for example, the phi f of theta phi equal d theta a phi, and you get 1/2 of sine sine theta. Sine theta over 2 times cosine theta over 2, 1/2 of sine theta. And so this f is basically, this f is the volume element with a factor of 1/2 in a sphere in the in momentum space. So I'm doing this calculation in polar coordinates, but it can be done also in the Cartesian coordinates. Similarly, you see what happened is that this magnetic field in momentum space has the form of a magnetic field of a magnetic monopoles. That is, this F is equal to 1/2 of R, sorry, P divided by absolute value of P cube.
Sorry.
Yeah.
So just a question that is maybe kind of related to Colin's question. So I think that like we can only get the Berry phase when we are using the phase space. But if we say that we just want to use the coordinate space, in that case, is it still possible to get this additional Berry phase?
If we yeah, I think it's going to be very it's going to be more difficult to formulate what I want to write down purely in coordinate space. The equation will be more complicated. I think at the end, I'm not sure if it can be actually done in a nice way. The only way I can incorporate this effect into a semi-classical dynamics is to work in phase space somehow. I haven't thought about this question very carefully though.
Thank you.
Yeah, you're welcome. But in this case, in this way of thinking, it becomes quite clear that we have now some kind of Lorentz force in momentum space. Due to the fact that we have now a magnetic field that has that is non-zero in momentum space. So this is a magnetic field of a magnetic monopole, and one of these properties is that if I integrate that magnetic field over a sphere, then I get 2 pi. So that's the quantization condition for a magnetic field of a magnetic monopole. But here it satisfies that condition in momentum space. So it falls down like 1 over p squared at large p, and in the center, p equal to 0, this Berry phase, or this is called Berry curvature. Berry curvature. Berry curvature is infinite at p equal to 0. So that means that what we have is that there is some Lorentz force in momentum space, and the way that Lorentz force appears can be expected by analogy. So let us write down the equations with the Lorentz force in the usual classical mechanics of a particle. P dot, is equal to E plus V. V is X dot cross B. Right. So that E is for static field is basically derivative of the scalar potential of X. So usually we write this equation in combination with X dot equal to velocity. So that is the epsilon P over dP. Now we expect another term, which is P dot. So it's a new term, P dot cross with the magnetic field in momentum space. So that, let me call that, yeah, in my notes, I call that omega, so that it's maximally different from B or F. This omega is the magnetic field of the Dirac fermion in momentum space, 1/2pp divided by absolute value of p cubed. One can check that this, you can check that this equation appears, it follows from the Lagrangian, which is px dot minus plus ai xi dot plus ai pi dot with a minus sign, I think, so that it's, and then minus epsilon p, energy as a function of p, and then also energy as a function of x as well. It's basically energy as function of x is only the scalar potential. But even without doing the variation of this action, we can see that we expect this new term to appear. So the analogy between coordinate space and momentum space is almost perfect, right? Instead of B in the second equation, B is the analogy of omega, this momentum space magnetic field, P and X. A0, of course, is energy in coordinate space, is energy in moment, potential energy is kinetic energy in momentum space. Yeah, so that's the equations that describe the motion of a particle, Dirac particles in external electric magnetic field, including the correction due to the Berry phase. Any question? So from now on, we can proceed almost classically. So we have used all information, the only information about the Diracness of the Dirac nature of this particle is in omega. Once we have this omega, we can now proceed as if these particles are semi-classical particle. But this, you have to remember the following, that the classical description breaks down at p equal to 0, because this omega becomes infinite. So we can write down the equation of motion for particle away from center of the center of momentum space. So if we have a Fermi surface, for example, the situation that we described for Fermi surface, and then we describe only degrees of freedom near that Fermi surface, these equations are perfect. But we should not ask what happened to things in the middle. But that's not very relevant, because these states are filled anyway with occupation number equal to 1. We don't have to worry about this. Okay, so this equation is can be solved. So this p dot and x dot, the velocity appear both in the left and the right hand side, and so we have to solve this equation in terms of x dot and p dot to get the velocities out of the field. So that can be done. So I'm just going to write down the the solution here. So V is x dot is equal to V of P. So that is V of P plus, let me write this way, E cross omega cos V. The solution are easy to check. And P dot. So here P dot then equal to, so except everything is now translated directly from, by replacing, for example, velocity becomes E becomes velocity. So V cross B cross E dot B becomes omega divided by 1 plus B omega. So here in this equation, you can see also the symmetry between coordinates and momentum when we solve this equation. So these are trivial equation. When omega is equal to 0, and omega equal to 0, x dot just become V of P, and P dot becomes E cross B, E plus V cross B. But because of the very curvature in momentum space, the solution to this, the expression of velocity through forces becomes slightly more complicated. Do we have any question? No, then I'm going to just proceed very formally and write down the kinetic equations. So here I write the kinetic equation by just replacing the velocity by what I've solved in the previous slide. That is Vp cross B cross omega plus Vp dot omega B 1 plus B dot omega dfp over dx plus E cross B cross B E dot B omega. So this is a kinetic equation that describes the motions of Dirac, a cloud of Dirac particles in phase space. F of P is their distribution function. That's something that is equal to 1 if it is a pure Dirac, Fermi-Dirac distribution at 0 temperature, be 1 or 0. In general, F of P is something between 1 and 0. Because these particles are fermions. One thing that distinguishes this equation, make it different from the classical equation, is that the phase space, turns out that this Liouville theorem is valid only if we assume the phase space to be 1 plus B dot omega times dp times dx divided by 2 pi h bar cube. That is the phase space that is conserved. And so the number of particles, the density of particles should be integral over d3p over 2 pi cube 1 plus b dot omega times f of p. So that's just some small modification. That basically there is some quantum correction to the notion of phase space due to the very phase of the particle.
Sorry, I actually have a question. So
yeah.
in this case, do we still have the relation between the x dot and p?
Between the x dot and p?
Yeah.
Yeah. So here is this relation. So x dot is almost equal to v of p. So here v of p is derivative of epsilon of p over dp, right? And that is p, a vector, unit vector pointing along the p direction times vf. So epsilon of p is equal vf, absolute value of p. So but there is something very strange, that the particle would move. There is a correction to the velocity. For example, this correction to the velocity, so of a particle. So there is some things that sometimes called anomalous velocity, new contribution due to the Berry phase to the velocity, called the anomalous velocity. Similarly, we have some new term in the equation for p dot. Particle move in a magnetic field. Previously, it's so let's forget about the denominator. It's sometimes cancelled by the phase space. This is a Lorentz force, but there is some new contribution to the Lorentz force that has a very important consequence. This new contribution basically is the following. So if I take a particle, so here, let me draw a diagram in momentum space. So imagine some kind of a Fermi surface, right? So this new contribution to p dot has something that is usual, Lorentz force, but plus E cross E dot B times omega. Omega equal P divided by 2P cubed, that's 1 over R squared. So this P dot is directed along the radial direction. It's the same direction as omega. And the amount, the magnitude of that is equal to E dot B. So if imagine the situation where we turn on in a system an electric and a magnetic field at the same time. And imagine that this E dot B is not equal to 0. And if you follow the evolution of each particle, they would have some normal, usual motion, like in phase space, like what it was according to the Lorentz force, etc. But in addition to that, in momentum space, we have a radial motion. With a magnitude equal E dot B in the direction equal to omega. So if we have, say, particle, if there was like a Fermi surface bordering the region where particles are in momentum space and where they are not, Then after some time, this Fermi surface will move outward to a new position. Like that. So it's, you see here that this equation means that the number of particles, if we define this number to be like this, then if we compute the number of particles, how the total number, that's the integral over x of that number, it will not be equal to 0, but it will be equal to some number times E dot P. The situation here should remind us of what happened in one dimension. In one dimension, we have just these 2 points. Turning on an electric field, basically move this point, the Fermi point, to the right, right? Or the particle receive kicks in the momentum, and this Fermi point moves to the right, and the number of right-handed fermion changes by the amount equal to E. In 3 dimensions, the change is proportional to E dot B. Now, this might be very counterintuitive. We have basically start from a kinetic equation, and what is a kinetic equation? Kinetic equation means that we follow the trajectory of particle and then see how they move in phase space. And this equation basically summarizes the collective motion of these particles in phase space. But this kinetic picture basically already should give us conservation laws, because we're not following trajectory of every particle. This particle do not appear from vacuum in this picture. And the resolution to this contradiction is that this equation, this kinetic equation, remember, it does not work near the center. So here, basically what happened is that we have some creation of new particle at the center, p equal to 0, when particles do not, this motion of particle cannot be described using the kinetic equation. Kinetic equation breaks down. So, but this particle somehow appears somewhere and filled the center of this Fermi sphere. Even if it's outer shell, every particle move outward. Particles would continuously reappear in the center, so that inside the Fermi sphere we have occupation number always equal to 1. We do not have a hole appearing with occupation number to 0 at the center of the Fermi sphere. So what happened in our case is that we have we can calculate and find this rate of creation, rate of particle non-conservation, and I'm not going to write down the precise coefficient, can be also found. The rate of change of the number of particles around Dirac point is equal to E dot B. So, but we know that in solid state physics, particle number, the charge has to be conserved. The number of electrons has to be conserved. So that means that if we have someplace particles, someplace in somewhere in momentum space, particle number is created. So Fermi surface move outward like this. Some another place it has to move inward. And that means that the Dirac point always appear in pairs. So the Dirac point can be classified by a number. This number is basically integral over 1 over 2 pi, integral over surface in momentum space times the Berry curvature in momentum space. And that can be equal to +1 in the case that we consider, but if we flip the sign of the Hamiltonian, make it minus sigma dot p, then this integral would be -1. So the Dirac point has some chirality. It can be left-handed or right-handed. So here, let's call that a right-handed Dirac point, and this is a left-handed Dirac point. The number of right-handed Dirac points and the number of left-handed Dirac points have to be equal to each other. And so that is how one can think about how one can reconcile the anomalies with conservation of charge. So the picture in 1+1 dimension, the picture is that the particle tunnel under the Fermi level from one point to another Fermi point. So equivalent in the case of the Dirac fermion, that tunneling is this motion is much more non-trivial to visualize, but basically it's also the same thing. There are some energy level which is largely negative, and one can in principle follow the motion of particle from one place to the other. When you turn on E and B fields, particle flows from the vicinity of one Dirac point to another Dirac point. So next time we will continue with in trying to describe how this anomaly leads to unusual effects, gets to non-trivial transport properties specific for these by Dirac by semi-metal. Okay, any questions?
I had one additional question about when we wrote down the kinetic equations, partial T FP. And so the prefactor of the second term, the VP plus E cross big omega, that thing, that's that's just the expression we derived for X dot, right?
Yeah.
And I'm just wondering if, I mean, could you also just write, would it be equivalent to just use the commutator between H and P? Does that give the same thing? H being the Hamiltonian?
Yes. So the Hamiltonian, one can reformulate it as the following. So usually, so this is a Lagrangian description, and in the Hamiltonian description, we can do the following. We can write down the Hamiltonian and then postulate commutator or Poisson bracket. So in a magnetic field, Poisson bracket between P is just the magnetic field, BK, something like that. Now we postulate the following: X do not commute. Up to this factor, this 1 plus B omega that I'm not going to write down. It has to be added, but qualitatively the Dirac fermions can be thought of as particles where the coordinates do not commute, as well as in magnetic field the momentum, canonical momentum would not commute with each other, but here the magnetic X do not commute, and then you write X dot equal the commutator of the Hamiltonian with X, I think at the end it will appear. Says I don't see it right away in detail how this term, for example, would appear, but I think it's I think it will appear.
Thanks.
Yeah. So yeah, I can post some references to the literature with this description.
Thanks. That'd be great.